we have a very, once again, exciting 90 minutes plus ahead of us. We will do something which we call the multiple linear regression. So it's partly some kind of an obvious extension of what you were taught last week on linear regression. That is the concept of seeing one y as a function of an x, making the line, as we've done, as I said last time, probably since third grade. But then last time we were taught all the statistics, the thinking, the modeling, the concepts that could go with such a line approach in many contexts, and should maybe also. Today is also kind of a repetition of what we did last time, because what we do today includes, in a way, the simple setting from last time. So, take this as a recap of linear regression with a bit of extra on top of it now. We have a 7-point plan, 3 before break, 4 after the break. Warm up with what we were taught last time, but in a context where we might need something more. This is a small data set. It is actually part of the R. You can find it there as, or a version of it at least, as called Airquality. These are daily measurements, environmental measurements in New York back in the 70s. Those are spring, summer, early fall measurements, not winter measurements. So from May to September. We have 111 days where we have recorded the amount of ozone. That's going to be our Y. That's the interesting thing that we'd like to know about now and in the future. And then we have measured temperature, radiation, wind. So I have a collection of 3 potential explaining variables or independent variables that potentially could relate to the ozone concentration, right? Now, after last time, you could have started to play around with this thing. So this is a recap, right? Here I express the linear regression model as it was told to you last time. And we could, and now of course I'm going to jump into R and do it now, but I brought this on the slide. Let me just look at the slide first and then jump into R and do some of the stuff. I have provided a version of the data file, that is this 111 long version of the data file. The file out there in R is slightly different, but we sort of cleaned out a few of missing data things, so just for you not to worry about that. It can be downloaded via the web page, right? Basically, a read-in, we have a look at the data, and actually this thing about only looking at the first 20, that's actually not necessary for us. Let's look at the whole bunch right away. And then I do some plotting, and I do a regression analysis. Or actually, I do a couple of regression analyses as part of it. Let's have a look. So, I read the data. First line. I hope you have seen some of this before. This is the realistic way, or at least one version of it, that data will hit you, that it hits you in a data file, and then you need some way to read the data file into R. This is one such way, using the read table function. Basically, this can read in anything on raw form, ASCII form. If you are able to use these two, combined with the third, the DEC, the decimal point, it works by default here, but Something went wrong. That's also the typical thing. I didn't make sure that I had the right working directory. Now I have. So I had a copy of this file on my laptop. We can use the str on the file to see we have the 4 variables. There are 111 observations of 4 variables in the data set. That's what I explained to you already. We could just, it's no bigger that we could just have a look. 111, y, x1, x2, x3, temperature on the Fahrenheit. We could use the head just to check the top 6 list. So this is just to make sure that my data set is sort of makes sense to me, right? Then let's do one of the major plot. We'd always do explorative data analysis in the beginning. Now I jump directly to plotting temperature, comma, ozone. So the ozone values versus the temperature. Conclusion. Well, it seems like the level of ozone increases with increasing temperature, right? Out of just looking at it. Let's try to quantify that and check whether the statistics support that. Because it's also pretty clear that there's a large variability from day to day. Even for the same temperature, we see very different levels of ozone, right? Is it really significant? What's your gut feeling here? Is it significant? How large is the correlation? How many think that the correlation is larger than 0.8? How many think that it's larger than 0.6? Come on, wake up. You were right. Pretty high correlation, right? Well, why don't we just right away fit the linear model then to see how it goes, to quantify the relation. So I fit, that's what you were taught last time, you could fit this linear regression model. And I just look at the R results here. How much does the ozone here is measured by log ppm, is already a log transformed scale. So it's a concentration measured on the log ppm scale. How much does that value change with increasing temperature? Here's the answer. That's the beta 1 hat, right? 10 degrees of Fahrenheit gives 0.7 on the log ppm scale, right? I multiply by 10, just one choice to tell the story, right? 10 Fahrenheit will provide 0.7 on the log ppm scale. So we expect on a day with 10 Fahrenheit higher temperature, a log ppm level 0.7 higher than the other day, which was 10 Fahrenheit lower, right? Is it significant, this relation? Have we statistically documented, proved that there is a relation between the temperature and the log ppm? How many would say yes? How many would say no? You're doing okay. P-value is extremely small. So clearly such a point pattern that we see, of course, could not happen by chance. We have measured to the degree, how likely could such a point pattern occur by chance on 111 points? Well, the probability of such a point pattern looking nicely linear like that is extremely small, right? So it would never, if you randomly sample 111 points, it would never look such nicely structured like that by chance. By never, I mean very, 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 very unlikely, right? So we have definitely, by the numbers, supported what we already more or less would conclude from the figure, that yes, they are related. We have statistically proved that. to the extent that it's possible to prove such things. The R squared, which is the square of the correlation. You may have missed that, and there are different formulas that was shown to you in the notes and in the slides, but nevertheless, it was told to you that the correlation of 0.75 that I calculated before, if you square that, you get this number, and in the output here it's called the multiple R squared. So, 57, rounding, 57% of the variability of the differences in the ozone concentrations, measured by log ppm, is explained by a linear relation to the temperature, right? So the linear temperature relation explains 57% of differences in the log ozone. It's a pretty high number, but it's also only a bit more than 50% of what's going on, right? But still, it's much more than 10%. Yeah. Good? So far, good enough? Let's just, for the fun of it, try to see what happens. Just to make you see that it's not completely stupid what we do here. Maybe it's just... Let's try to add some random numbers and see what happens if I try to model the ozone as a function of random x input. Not related at all, I mean just purely random. I'm emphasizing, I'm only doing this now for illustration. It's not something we would do as a part of a data analysis or a modeling approach. I emphasize that. It's just for illustration. So, I simply simulate 111 random normal numbers unrelated to anything here, right? I call it noise and I put it in my data set. Noise for white noise. I plot correlation, slightly negative, quantitatively very small, it seems, right? What about the analysis? Well, we see if I'm lucky. I mean, in 5% of times, I would have to explain myself, right? 5% of the times, it might come up significant. But not today. Noise, not significant, right? It's just to let, yeah, this makes sense, right? Now, we couldn't prove, and we shouldn't, of course. So it's fine. It seems to work, what we're doing here, right? At least apparently. Now back to the motivation towards what's going on today. We also had wind information, and we also had radiation information as two other potential X's to explain the log ozone, right? Let's try to do it one by one. Just why not? I mean, I gave you a hammer last time, the regression hammer, the 1x regression hammer. We can use it by just hitting several times, right? It's not wrong. If we have nothing else, we hit with whatever we can hit with. Kind of big words on a morning, but nevertheless. Something. Actually, I would like to change this. This was not the way I'd like to do it. Yeah. Here it is. Here it is with the right names. More wind, less ozone. Yeah, probably if you had your environmental whatever courses and a bit of physics and a bit of common sense, that doesn't then in a way surprise us. But it's nice to document things because we cannot win a Nobel Prize for just speculating, you can say, and say, I believe it's like that. Often we have to document things by numbers. Is there a relation between the ozone and the wind? if we take it by like that, it's negative. It's even stronger. The size, at least on the scale, sorry, it doesn't make sense to conclude like that. It's a different scale, so I couldn't compare the size. But at least the p-value is very clearly small also, right? And finally, let's have a look at, and this one was also, I missed that one when I was going through this. I'll try to upload this right after the lecture such that you have the most recently one when you hit the exercises. How about ozone versus radiation? Well, higher radiation, more ozone also, right? The regression analysis, third time I do this, or actually the fourth time, 3 with the X's and 1 with the noise. Is there a relation? Yes, there is. At least when I look at them one by one, right? Well, that's what we've been talking about so far. Now, the point is, it seems that all 3 things are influencing the ozone, right? So it's not really, what you could say, it's not really satisfactory to have 3 separate models. We should aim at taking all 3 things into account at the same time and make a joint model somehow, right? That would be the more meaningful approach, because apparently the real-life phenomenon that we are studying here are more complex than just Y depending on one thing. It depends on more than one thing, apparently, seemingly at least. So we have to sort of face that complexity to be able to do some real-life work with this. And just before we jump into it, here, it's very easy, and the function is prepared for that. It's very easy in R to formulate this extended model that we're going to learn about today. We can simply plug in some more x's by pluses. That's the syntax, right? We can just let the ozone depend on this plus this plus that. In a way, in principle, as many things as we would like. There are some math limits here, but in principle, many things. And there are some consequences, and there are some things to think about. So that's the topic of today. Yeah, that's the simple linear regressions on the other 2. I did that in the R. So we're ready to move towards what is called the multiple, for obvious reasons, linear